Today we have a nice talk by a nice speaker from our group. Filipa is going to present. Filipa is a postdoc here. Everybody knows her. She's going to present her recent work with Julio and Juani and someone else.
Yes. These people. Yeah.
Yes. Okay. And about very abstract and complicated quantum computing things. Okay?
Okay. Hello, everyone. Thank you for coming. And thank you, Danny, for the introduction. Yeah, like Danny said, this is work I did with Julio and Juani, and also Marcus from the University of Cologne in Germany. And yeah, the title is maybe a bit of a mouthful, like Symmetry-accelerated classical simulation of Clifford-dominated circuits. Hopefully, by the end of the talk, this will become clear. And if you want to check the archive, it's just scan the QR code. Okay, so I'm just going to give you a brief overview of the presentation. I will start with some motivation. Why we are interested in classical simulation and these kind of things. Then I'm going to give you some background concepts that you're going to need to follow the presentation, and then at the end I'm going to give you a summary. I'm not going to give all of the theoretical results, but I said the most important theoretical results and how we applied it to interesting situations. Okay, so this is the overview, and I guess the first question, I had this really big title, started something like Symmetry-accelerated classical simulation, and I guess the first question I could ask is, what is classical simulation? What do I mean by classical simulation, or what do you think about when I say classical simulation? So I give you a circuit, and I ask you to simulate it. What would you try to do to simulate this classically? I give you a quantum circuit. I say, please simulate this for me. What would you try to do?
Go to Proteus, write the circuit, and try and see if I can run one Proteus.
You multiply matrices.
Yes.
Yeah, but what would be your goal? What would you compute?
The final state?
Final state.
Or some expectation values.
Or some expectation values. Okay, so basically the idea behind classical simulation is I give you some quantum computation, usually in the form of a quantum circuit, and you try to use fully classical resources to simulate it, but the notion of what it means to simulate varies a lot, right? So one idea could be you try to compute output probabilities of this quantum circuit. This is usually called strong simulation, and you can do the exact version of it. You try to compute exact probabilities, or you can try to compute approximate probabilities. Okay, this is usually what people refer to as strong simulation. A different alternative is you try to come up with some kind of classical algorithm that gives you samples with the correct distribution from this circuit, right? And this one is usually referred to as weak simulation, and again, it has an exact version where you get the classical algorithm to give you samples from the exact output distribution of the circuit, or an approximate version where you try to have it give you samples of a distribution that is epsilon close to this distribution according to some metrics. And if you think about it, if you can compute probabilities exactly, you can also sample, right? Because if you at least if you can compute marginals, you can find what's what is the probability of getting the first qubit to give 0. You flip a coin based on that probability, You find the outcome, then you compute the next marginal. What's the probability of getting 0 from the second qubit, given that the first qubit gave some output, and you flip a coin based on that distribution. So if you can do the first one, you can do the second one. And we know that, generally speaking, computing probabilities is a much harder task than sampling. And also, if we think about this a bit further, if I give you a quantum computer, in general, quantum computers won't even be able to compute probabilities exactly. Like when you ran a circuit, what you get is a sample, right? You don't get some probability, you get some samples. So in general, the task of computing probabilities is sharply hard, and sampling, we say it's like in BQP, which is kind of the hardness associated with quantum computing. And then I think someone also talked about like estimating expectation values. And this usually, just a second, this usually has to do with like, this is called epsilon simulation, and it's weaker than all the other ones, and has to do with like you try to estimate some expectation value to some additive error. Go ahead.
So just to be clear, you were saying that the sampling using a quantum computer is in BQP, but computing the probabilities is not?
Computing probabilities is usually sharply hard.
Okay.
So it's like if you can compute probabilities, you can solve very hard problems. Yeah. So usually like the quantum computers won't be able to, in general, be used to compute probabilities exactly.
Okay.
Right? So it's very different, like the idea of computing. Notice the choice of words. This is a nuance that people, when they're careful writing papers, between the choice of word of like computing and estimating. So computing is sort of implying you compute it exactly, or if you compute it approximately, it's usually to some relative error or multiplicative error, so a really small error. And here, when we're talking about estimating expectation values, is an additive error. So this is much easier than the other two. So because you can understand, if you can sample exactly, then you can estimate expectation values. So quantum computers can do this, right? You can just gather a bunch of samples and use it to estimate some expectation value. So basically it goes like this. If you can do that, you can do that. If you can do this, you can do this. So they're successfully weaker. And so these are the different tasks, and it's important whenever you're reading like a classical simulation paper to understand like, okay, the algorithm that these authors are proposing, which of the tasks is it? That's the first thing that is important about classical simulation. I guess the second question is why? Why is studying classical simulation interesting? And here there are many different reasons. I selected just a couple. So one reason would be that we understand a bit better where quantum advantage comes from and what this mystical quantum advantage regime is, right? So we have seen in the past, like Google making this quantum advantage claim, like here it is, we made this experiment, it would take a classical computer a long time to compute it, and then someone comes along and writes a really good classical algorithm that actually does that really fast. And so designing better and better classical simulators allows us to try to trying to sharpen where exactly is this quantum advantage regime that it's very hard to pinpoint, right? I guess a second motivation would be to try to verify or validate how quantum hardware is working. So right now we're starting to have first prototypes and things like that. If we want to validate and see are they working correctly or not, if we have very good classical simulators, then we can verify them by simulating the same thing that they're trying to execute, and we can validate this hardware. Of course, if we are using the classical simulator to verify some quantum hardware, and this is possible, it also means that the hardware is not exactly doing something that gives you quantum advantage, right? So there's this tension between the two things, but it's another useful application. And another one is that studying classical simulation allows us to try to maybe understand what are the quantum resources or the physical phenomena or whatever, that is kind of giving us this quantum advantage. What are these things that, because if we understand, okay, these circuits I can simulate efficiently, so there has to be something that they don't have, that is what gives me quantum advantage. And so if we are able to understand this better at a foundational level, hopefully this will also inform like the design of better quantum algorithms if we understand these mechanisms that are at play and giving us quantum advantage. And as a perfect segue from here, we enter the background. And for those that attended one of my journal clubs in the past, we have talked about the Gottesman-Neal theorem. And this is, don't worry, those that didn't attend, I will get into it. But basically, the Gottesman-Neal theorem is a very important theorem that says that Clifford circuits is a class of circuits that are efficiently classically simulable. Okay? And what are exactly these Clifford circuits? So these are circuits that you initialize in a computational basis state. It can be the all-zero state without loss of generality. And you measure in the computational basis. And in the middle, you only allow this set of operations that are called Clifford unitaries. And Clifford unitaries are form a group and are this special class of unitaries that basically take Pauli operators to Pauli operators. So one example, as we saw in the journal club, is, for instance, the Hadamard gate, which basically so they take Pauli operators to Pauli operators under conjugation. I didn't say that. So basically, if you apply a Hadamard to a next gate, it will give you a Z. And if you apply it to like a Z, it will give you an X. Another example is the S gate, which is just this diagonal gate that has 1 and the identity in the diagonal. It's a 2-qubit gate. And again, like it's diagonal, so it's pretty easy to see that it maps, the Z into itself. So if you do this, it maps it to Z, and I think with dx, it maps it into y or minus y. There could be a sign here. But yeah, and so these are just some examples. Then you have also like the C0, the control Z. These are all examples of Clifford gates. And they all have this property. And so it's very interesting that if you have only this set of operations available to you, you can show that these circuits can be efficiently simulated classically. And yeah, so this is interesting because Clifford circuits can be very entangling. So it means that entanglement, we know it's necessary for us to have quantum advantage, but clearly is not sufficient because these circuits can be very entangling. Like they can generate bell pairs and things like that. So you can use just Hadamard and C0 and generate a bell pair from the 0-0 state. And yet we can simulate them. So there has to be some other resource that in a sense is necessary for quantum advantage. And we know that basically universal quantum computation requires what is called a non-stabilizer operation, so or a non-Clifford unitary. So we can either have like a non-Clifford unitary or some non-stabilizer state, and we can do universal quantum computation if we have access to such a resource. And some commonly used examples are the T-gate. So this is one. And the other one is the control Z gate, which is just a bunch of ones and then a -1. And this is like locally equivalent to the Toffoli gate. So you can create the Toffoli gate from this if you just apply a Hadamard in one of the qubits. So these are common examples, and basically what it means is if you have access to operations in the Clifford group and then you add one of these gates, then you can do any kind of quantum computation with this set of operations. And so the question we are interested in is, okay, so let's say we have some general circuit that looks kind of like this, so it has n qubits. And then it has some Clifford unitaries that I grouped here into the green boxes. So the green boxes are Cliffords. And then we have some non-Clifford gates that are the red boxes that are, interspersed here between these Cliffords. So we know if we only had green, we could simulate this efficiently, but now we are like putting these kind of red boxes, these non-Clifford operations here. And in general, like I said, like if you have Clifford plus T or Clifford plus control Z, you can write any quantum computation using that set of gates. So the question now is, how do we simulate something that looks like this? And here I'm writing things a bit more generally, right? I'm admitting that maybe the circuit has different kinds of non-Clifford gates, but in general, you could also just have T gates and everything would be just single qubit boxes and things like that. So how would we simulate something like this? Does anyone want to try to guess, or should I? Okay, no guess. So one thing we can try to do is, okay, we have this non-Clifford gate. Why don't we just write it as a sum of a bunch of Clifford gates, right? Because we can do that, right? We can take these non-Clifford gates and just decompose them as a sum over Cliffords. And we can do this with each of these boxes. And then we can combine everything. And in the end, we would have this quantum circuit. The whole quantum circuit could be written as some sum over Clifford unitaries, right? And now we have a circuit that is written as a sum of Clifford unitaries. And what we can do is, we know that Clifford circuits are efficient to simulate, so we just simulate each of these circuits associated with each of these terms, and in the end we combine the results in the classical computer, do some classical processing, and we simulate the quantum circuit.
Sorry, Filipa,
yes.
The coefficients in this sum, are they real, complex?
They can be complex, yes.
Okay, so the problem, because if they were real, there would be no problem in simulating it, no?
There would. We will see why. Yeah.
If they were between 0 and 1, this would just be a probabilistic classical simulation of a Clifford circuit, would it not?
Yeah, okay, sure. In that sense, yes. But this is in general like, so that is a very good question. Even if they were like real, what you see in some simulators that kind of try to do a similar approach to this, not exactly this, but you can do the same thing with states, right? You can assume that what you have are magic states at the beginning, and you try to expand the states as a sum over density matrices that are just the density matrices of stabilizer states. And in that case, you have real coefficients. But the point is that what you actually have is not a probability distribution, it's a quasi-probability distribution. It has some negativity, and because it has some negativity, this picks up an exponential that, you pick up. So here in the unitary version of the thing, this in general can be complex. So that there's that added nuance. And so this was originally, okay, so the slides are being cut a little bit, but this was originally proposed by Bravi and a bunch of co-authors. And they called it a very straightforward name, which is just the sum over Clifford simulator. I think very suitable, and it's easy to understand why. And so here the important point, which also addresses the question you just asked, is this is the runtime of this algorithm, where basically, so this algorithm doesn't do exact simulation, does an approximate simulation. So we see some parameters here that have to do with like the error of the approximation, some probability of failure, and it's just the number of qubits. And then we have here this square of the one norm of the coefficients. And basically that's where the exponential scaling is hiding, in that square of the one norm of these coefficients. And So if we want to do this simulation as fast as possible, it's kind of intuitive now to understand what we have to do. What we have to do is try to kind of find the decomposition that is optimal. And optimal in this case means the decomposition that's going to give us the smallest one norm. And if we find that, we find the best possible runtime. Yeah, go ahead.
Just to make sure I'm understanding this, so for each of the non-stabilizer operations, you're decomposing this as a weighted sum of Cliffords in the circuit, and then you're basically simulating many runs of the action of this circuit for each decomposition into just straight Cliffords, and then at the end you somehow sum up the statistics for...
Yeah, so in the sense what you do is, so you write it as a sum over Cliffords. Now we have Clifford circuits. Each of them you can run in polynomial time, right? Because it's efficient. So you run them, you get the output states of this, and then you know how to combine them, and then you use the information to get samples.
But it seems as though you would get like combinatorial growth in the number of Clifford circuits you have to simulate, because for each of these stabilizer operations you're kind of multiplying by a factor of however many Cliffords you need to decompose it into.
Yes.
Why?
No, that's the point, right? So if every non-Clifford gate, for example, you could, these coefficients were non-zero for all the Cliffords, right? This is bad, because your norm there, this would be exponentially large. Right? So what Filipa is looking is exactly saying, okay, if I do this approach, and I decompose it, I'm clever enough to decompose it in such a way so that the number of terms in this decomposition are small, then I simulate a small number of circuits and then I put them together. No?
Yeah, and it's not necessarily the number of terms, because actually the zero norm and the one norm are not necessarily related. So it's like...
What I'm saying is, okay, typically, for example, if you take the one norm, imagine that every coefficient here is non-zero. Then the one norm is going to be, imagine everything is one, for example.
Yeah.
And the one norm is going to be very big.
But supposing that for each of these like non-Clifford gates in the circuit, your decomposition only has two non-zero coefficients, and you've got n of these non-Clifford gates, then you're not going to have to basically run 2 to the n many.
No, like there's a better way. That's the point. If you do it like this, yeah. So for instance, a good example of that is the T-gate. The T-gate can be decomposed into a sum of identity with some coefficient and the S-gate with some other coefficient. This is known to be like the optimal distribution in terms of the one norm, and interestingly for the T-gate, the tensor product of that decomposition, the optimal decomposition is just actually tensoring the decompositions for that particular gate. In general, that's not true. So you're going to have like 2 to the number of gate terms, and yet the scaling is 2 to the 0.228 to the number of gates. So it's like it has a coefficient smaller than 1.
Okay.
So that's why this approach is interesting. Like it doesn't give you the naive scaling that you would think.
Okay.
Yeah. So this kind of motivates the defining this quantity, which is the stabilizer extent. And the stabilizer extent is just defined precisely as the minimum of this one norm squared for some matrix M. Right here we define it for general matrices, not necessarily unitary, just because in the context of our work, it's necessary at some point to allow for other more general matrices. And yeah, so this is the stabilizer extent, and then one might think naively that, well, okay, like this is minimizing the one norm of some decomposition, this is a second order cone problem because, like I said, these are not necessarily real. So this seems pretty simple, just bring your classical computer and find the decompositions. But the thing is, the reason why this is hard is because actually the size of this Clifford group scales super exponentially with the number of qubits. So basically, until our work with Julio and Juani and Marcus, people were able to compute the stabilizer extent for unitaries of up to 2 qubits, more or less. And then from 3 onwards, this size is enormous. You would need a lot of memory, and it becomes a problem. So this motivates this idea of, okay, but maybe the unitary that I want to decompose has some kind of symmetries that allows us beforehand to know that we don't need to search over the entire Clifford group. Maybe we just need to search over a subset of this group. And this will make the problem much simpler, right? And so now we get into our result. And what I'm going to do is, first I'm going to give you like the formal statement, the way we stated it. And then I'm going to say it in a completely informal way so that you understand basically what the result means. So what we do in the paper is we define this quantity that we call the G-symmetric stabilizer extent. Okay? And so this G-symmetric stabilizer extent is defined in the following way. We have some symmetry group G, and then we have this subset of Clifford unitaries that are invariant under this group, right? And we call this Cn with G there, okay? And so the G-symmetric stabilizer extent of some G invariant matrix, so it has to be a matrix that is also invariant under the action of G, is defined as the minimum of the one norm, like everything is the same, but now we just search over this G invariant subset of Clifford unitaries, right? So it's the same definition as before, but now we're saying, we have some matrix that has some symmetry G, and we are minimizing only over the subset of Cliffords that are invariant under that symmetry. And this is our definition for the G-symmetric stabilizer extent. And we're going to talk about some symmetry groups, like this one is just, the group generated by complex conjugation in computational basis, and the group generated by diagonal Paulis. And then for those groups, we have the following theorem that we call just the strong symmetry reduction, which is if we have these 3 symmetry groups, so the group generated by complex conjugation, the diagonal Paulis, and then just the composition of the two. Any unitary that is invariant under the action of this symmetry group G, we can prove that the stabilizer extent equals the G-symmetric stabilizer extent. So what is this telling you informally? Very simple. If we have a unitary that is real, or that is diagonal, or that is real diagonal, it admits an optimal decomposition in terms of just the reals, the diagonals, or the real diagonal Cliffords. So this is the informal statement. And this, you can see, is going to help us a lot, because in blue, you see the size of the full Clifford group. And then you see, maybe the real Clifford group is not much smaller, but in the case of diagonals and real diagonals, the difference is perceivable. So this is going to make finding optimal decompositions much simpler. And okay, at this point I want to stop to see if there are questions. And if there are no questions, I'm going to say that there is actually a very nice question that you could ask right now. And Ria cannot ask because she knows.
It's very stressing, because if we have a question, we think that it's not going to be the nice question.
The nice question.
But okay. One question is, why these symmetries?
Okay.
And why not
Good.
other symmetries
Good. That's almost the question. The question is, you know, like, can we apply this to other symmetries? It's basically, it's an interesting question with not so easy answers. So it's not exactly clear. That's one thing we leave as an open question to try to understand what exactly are the symmetries that allow this strong symmetry reduction. There's one thing that we can understand is that if we have some symmetry that leads to a subset of Cliffords invariant under that symmetry that doesn't span the whole space, this could give a problem, because if it doesn't span the whole space, it could potentially, you could not even find like a unitary that's decomposed using those Cliffords. So those kind of symmetries wouldn't work in principle. But then even if you find some symmetry that gives you a subset of invariant Cliffords that do allow you to decompose your unitary, it's not so clear that this theorem is going to hold, and actually in general it will not. Here I'm going to show you a counterexample. So these are the so-called F-sim gates. They're very famous gates that you can write as you see here, and I mean an example of these gates is the I-swap is a particular instance, and in the first supremacy paper by Google, they use the two-qubit gate that they use is it's a gate of this form with specific parameters. I forget exactly what the parameters are, but these gates, you see them in a lot of places, and if you look at it, you can see two symmetries. You can see that the gate is invariant under qubit permutations. So it's a two-qubit gate, and if you permute the qubits, it's invariant under that. And it's also invariant under transposition, right? If you transpose the matrix transposition, right? If you transpose the matrix, it's invariant. And what we did is, for these two-qubit gates, we computed the stabilizer extent using the full Clifford group. So this is how the stabilizer extent looks like for arranging the parameters from 0 to 2 pi and 0 to 2 pi. And then what we did is, okay, now let's restrict ourselves to the set of Clifford unitaries that are invariant under transposition, and let's try to optimize. And then we took the ratio of the value that we observed with the true value of the extent, and if they were giving the same thing, we would have to have 1 all over, and that's clearly not the case. So, and then we did the same for the permutation invariant case. Let's find like the permutation invariant Cliffords and use those to try to find the decomposition. We found the optimal decomposition using only those, and we see that it also doesn't match the true value of the stabilizer extent. So, yeah, this is just a nice counterexample showing that the strong symmetry reduction in general is not going to hold for every symmetry. Good. So let me just check how I am for time. Okay. What can we use this for? Like I said, I mean, we can use it to compute the stabilizer extent for larger unitaries than before. And here's an example. So we computed the stabilizer extent for these controlled phase gates, which are just diagonal gates that have some e to the I theta as the last entry of the diagonal. And you can see from this plot that actually we were able to compute the extent for gates up to 7 qubits. And so, okay, for instance, this is for 1 qubit, and this is just the Z gate, which we know it's a Clifford, so it has an extent of 1. And this is the S gate, so it's this gate here. Actually, this is S dagger, that's the S gate. And it's also a Clifford, so it gives an extent of 1. And yeah, we just see how the stabilizer extent changes for different qubit numbers and different rotations. And actually, these gates are quite, you see them a lot in the literature in different contexts, and this is just an example. So this is the example of a 5-qubit circuit that is implementing the quantum Fourier transform subroutine. This would be like the textbook way of writing it if you go to Nielsen and Schwang or something like that. This would be how it would look like. So we see that it has some Hadamards, these are Clifford, but then it has some blocks of non-Clifford gates, of control non-Clifford gates. And while before what we would have to do is find the decomposition of each of these gates individually, now we can actually decompose each of the blocks, right, together. So we just combine and we decompose each block. And you see here the stabilizer extent for each of these blocks. And then if we take the product of the extent, we get something like 11.7. And usually what people do when writing quantum circuits, and also often when simulating, they would write things in terms of the Clifford plus T set. And we try to find in the literature like how many T gates it would take to write this using that gate set. And it would be something like around 60 T gates. And if you calculate the extent of decomposing 60 T gates, it would give something like 10 to the 4. So this means that if you remember, like the extent precisely gives you the runtime of the algorithm. So we are saying that using the algorithm by Bravi et al., using the decomposition of these gates directly would give a speed up of around 10 to the 3, so 1,000 times more or less. And this only grows like the bigger the circuit gets. You'll only see this effect more and more. So the point is, like, it's better to try to decompose the circuits natively in whichever gate set they're natively written, than maybe try to write them in the Clifford plus T or Clifford plus Toffoli or whatever, and then try to simulate. Yeah, and our work allows to do that. And then, yeah, another application has to do with studying this type of states called hypergraph states. And I mean, here you have the formal definition, but the idea is really very simple, which is, and I'm going to give you just an example with, for instance, 5 qubits. So you can write some hypergraph that has 5 vertices. Each vertex you're going to associate with a qubit. And now you can create some states. So if you don't have any edges, you just assume each qubit is in the plus state, and you just have this state. But then you can start bringing in entanglement, for instance, and you could apply, for example, a control Z gate between these 2 qubits and between these 2 qubits. And so you would apply like a control Z gate, I don't know, 1, 2, 3, 4, 5, say 2 and 3, and 2 and 5, right? And you can create states by applying these kind of gates. You can do a 2-qubit interaction, but you can also do maybe a 3-qubit interaction. And I don't have colors. I think maybe here.
Here in the table.
Yes. And this is empty, and this has only green. Sure, that works. But maybe we can, instead of just considering these kind of edges, we could consider like a hyperedge that connects these 3 qubits, and this would correspond to applying a control Z. Or maybe we want to do like a hyperedge of size 4 that connects 4 qubits, and that would be a control Z gate. So, and you can create this kind of graph or hypergraph state. So if you only have like edges connecting 2 qubits, you get a graph state. And if you have hyperedges that involve more than 2 qubits, then you have a hypergraph. And so what we did is actually we focused on hypergraphs where the hyperedges all have order 3, so all involve 3 vertices. And yeah, here's also like a 5-qubit example, and you can see that basically this just corresponds to decomposing the control Z gate, which is known has a stabilizer extent of 1.77777. And interestingly, you can create also this kind of hypergraph state where you have 4 different control Z gates. So you have 4 of them, and this has exactly the same extent as the other one. So what we're saying is that if you wanted to simulate some kind of computation on this hypergraph state, it would cost you exactly the same, one of the other. This just shows how this physical resource of magic or non-stabilizerness, which is what we call these resources, it's non-intuitive to quantify it. And then if you have maybe a hypergraph state that is generated with this kind of combination of hyperedges, then you have a bigger extent than the last two, 2.56. And here is a different example where, again, you have like 4 order 3 hyperedges, but they're interacting in a different way, and this is more costly than the other one that also has 4 hyperedges. And why is this interesting? This is interesting because it is known that if you have specific types of hypergraph states, these hypergraph states, you understand that they have both entanglement and non-stabilizerness. So they have 2 resources that we know are necessary for quantum computation. And if you have a kind of lattice that looks like this, where again, like the vertices are qubits, and then you have like each triangle is a control Z, and you can create this kind of lattice. This is known as the Union Jack state, and it is known that you can do universal quantum computation on a state like this just by doing Pauli measurements on the qubits. And Pauli measurements are stabilizer operations, so all the magic is imbued in the hypergraph state. And the point is, if you take a hypergraph that looks like this with n qubits and you decompose each of the control Z gates individually, you would get a runtime for the algorithm. You would get a stabilizer extent that would be 2 to the 1.6601 n. But if you take a decomposition of this entire yellow square, which we can do because it has like 5 qubits, and we can decompose unitaries of 5 qubits, then and then you basically take that building block to create the entire hypergraph state, then you get a runtime scaling that goes like this. So we significantly lowered the cost of simulating a measurement-based computation that is based on this kind of hypergraphs. So we have, as you see, like an exponential improvement from up there to down here. And this kind of finishes everything that I wanted to say. And the take-home message is just this idea that symmetries are a powerful tool to scale these classical simulation techniques, and hopefully also allow us to gain a deeper understanding of where is this quantum advantage regime. And that's it. Like, if there are questions.
So you mentioned that it doesn't work for every symmetry, but so far you only have like the Paulis and the conjugation.
Yes.
Do you have any idea? Because these are very specific. These are finite symmetries, and they're like I think for the Paulis it's even billion symmetry. No? So if I give you symmetries corresponding to like. Is the non-simulability, or at least on the symmetry group that you apply, Does it have to do with the fact that it's a billion or not a billion or finite, or do you have any intuition about that?
No, I think, so we tried to do some brainstorming about this in one of the meetings, and in the end we came up with the idea that that's going to be our follow-up paper, try to understand like what are the symmetries that work and what are the symmetries that don't. But yeah, we don't have like a clear answer at this moment. There seems to be some idea that there might be like a link of this with like T designs and maybe some connection there that will help us gain some understanding into this. Marcus seems to have some intuitions as to which symmetry groups might work and which might not, and I think the idea is to try to pursue that in the future. Yeah.
Have you thought about like other simulators, like stabilizer rank and stuff, or you could do similar things?
So, yeah, so in terms of simulating Clifford-dominated circuits, there are different approaches. The sum over Clifford approach decomposes unitaries, things like stabilizer rank and things like that, decompose states. The advantage of the sum over Clifford simulator is that, generally speaking, it's faster because it handles vectors of smaller size in general, and it's also more general because for the simulators that involve basically decomposing quantum states, this comes from the fact that you can, no, I have to write here. You can basically, you have a circuit that has some T gates, and you can show that you can actually, this is acting on some state psi, and you can show that you can actually implement the same transformation with a scheme like this, which only has Clifford unitaries and stabilizer operations because it's a C-naught, this is an S-gate, and this is a computational basis measurement. And this, basically what you're putting is you're putting all your non-stabilizers in the states, and then once you have like done that for all the T's, you're gonna have a set of T states that you then decompose. And you can apply a stabilizer rank kind of procedure. But in general, doing this requires that your gate admits some kind of injection gadget that you can do. So the simulators that use states are also more restricted in that sense, because that's not going to be possible to construct something like this for every state. Whereas some like gate, some rotation gate with a really small angle, you can have it there and just decompose it, right? This just to give an impression. I know I haven't answered your question yet, so that's one motivation to focus on the sum over Cliffords. But your question is like how to, if we thought about using these kind of ideas for the gadget-based. These are often called like gadget-based approaches where we decompose the states. No, we didn't think about that. The problem of finding exact decompositions of magic states has another problem, that is the stabilizer rank. The one that goes with the exact stabilizer rank involves actually minimizing the zero norm. So in that case, what we want to minimize is actually the number of terms. And generally speaking, that's a non-convex optimization problem. So it has that added bonus of difficulty. You could try to use like the approximate stabilizer rank, but then the whole point actually of defining the stabilizer extent. Here I motivated it after defining the simulator, but actually the stabilizer extent the definition originally came from the fact that it's actually an upper bound for the approximate stabilizer rank. So all these things are connected. And actually, if you compute the stabilizer extent and if you find the optimal decomposition of unitaries, you know that that's an upper bound for the corresponding quantum state. So in general, like if you have some unitary U and you have some state like this, for example, in general we know that this is true. So solving the unitary problem kind of gives you an upper bound for the other one. There's a connection. But no, like we haven't thought specifically of using the idea of symmetries for the state version of the problem.
Yes.
Yeah.
So here the main problem is that we cannot simulate every qubit gate. But what is the difference between the Harman gate and the X gate, for instance?
Can you repeat the question again? Sorry.
Yeah, so I think here the main problem is that we cannot simulate efficiently every qubit gate. So we have the Harman that we can efficiently simulate it, but we have others like the X gate and the Y gate that we cannot.
No, they can be simulated. Yes, the X like Pauli's also map Pauli's into Pauli's. So Pauli gates are going to be efficient. Clifford gates are going to be efficient. So you need something that's outside of the Clifford group, and that's something like the T gate that I mentioned. Like, so these are the gates that are challenging. Like these kind of gates, right? The T gate is not a Clifford gate, does not map Pauli's into Pauli's, and control Z is also difficult because it's not a non-Clifford gate.
So then, I was also wondering because if we have just one qubit, we can express any gate as a combination of the Pauli matrices. So then if we have like the basis only has 4 elements and we can efficiently simulate those 4 elements, why not the size of the Clifford group for one qubit is 4, so it's higher instead of 4, I think.
Okay, so the thing is, we could also do a sum over Pauli matrices in general for n qubits. This would give you the Pauli group would have, if we mod out the phases, 4 to the n elements, like you're saying. But the point is that if you try to find a decomposition just using Pauli matrices, you're not going to find, in general, the optimal one. So you can find a decomposition where here you have only the Pauli groups, has only 4 to the n, and here are only Pauli operators. But then this, the one norm of this is going to be, it's not going to be optimal, and it's going to give you a way worse exponential scaling. Yeah. So for instance, that is true for this T gate that, like I said before, like the optimal decomposition is some coefficient here plus another coefficient here with the S gate. You can also find a decomposition where you write this as the identity plus Z. But this is going to have a larger one norm than that one. So this one is better for the simulation.
Okay, any more question? No? Everything clear?
If it's not, you can ask me afterwards.
We are all masters of symmetries and Cliffords and...
No, but the problem about which symmetries work is interesting.
Yeah, that's an interesting question.
Also, it's interesting if I give you a unitary and you don't know the symmetries.
Yeah.
The symmetry, find the symmetries and know if it works.
Yeah. That's true.
It's not a trivial problem. It's nice.
It was never trivial. If it was trivial, it would have been known already.
Yeah, exactly.
No interesting.
Exactly.
Okay, so thank you very much.
Thanks.